Now we're going to look at some of the effects of of intermolecular forces. So of course, the existence of solids and liquids, but other things happen because of intermolecular forces. These include surface tension, viscosity, and capillary action. So these are a couple of cool pictures. This is a spider web, and it's got dew on it. Dew is when the air gets cold and water that was previously in the air condenses. And that's why you go out in the morning sometimes and the grass is wet. It wasn't the sprinklers and it didn't rain, but the grass is wet and the car's wet and everything's just damp because the dew condensed out of the air. So here, the dew on this spider web is forming little droplets. And then this is a neat picture too. This is a paperclip floating on water. That just doesn't seem like it should happen, right? Because metal, unless it's like shaped like a boat or something, should sink in water, right? But here it's floating. And you can kind of see that there's like an indentation. So it's almost like there was a cover on the pool and you've got somebody laying on top of the pool cover, right? They can't go through the pool cover, but their weight is pushing it down. And so we'll see that surface tension sort of forms a skin on top of the water, and that's what the paperclip is sitting on top of. So surface tension. The tendency of liquids to minimize their surface area. We can quantify this, measure the energy required to increase the surface area by a specific amount. So just as an example, water has a surface tension of 72.8 millijoules per square meter. So if you took water and you were to increase its surface area by a square meter, which is pretty big, it would require 72.8 millijoules of energy to do that. Here's another picture demonstrating surface tension. This is a trout fly. That is more dense than water, and yet it can sit on top of the water. You may have seen water skaters, little bugs that skate around on top of the water. They can walk on water. So how does this work? Well, here we have a two-dimensional illustration of particles. Let's call them water molecules. So if we look at a surface molecule, it has interactions between its neighbors side to side, and then also with the neighbors on the inside, to the interior. So this is the surface of the water. If we look at a molecule that's inside the water, deep down inside, it's attracted in all directions by other water molecules. So this particle here has higher potential energy than the one on the inside because it has fewer attractions to other molecules. It's not as stable. If we want to increase the surface area of this liquid, we have to push aside the surface molecules, and some of the interior molecules would have to become surface molecules. They would have higher potential energy, and that's going to be less stable. So that requires energy. And things don't like it when you have to get energy from somewhere else. So the water will form a sphere because that is the shape that gives you the smallest surface area for the volume. A cube or a sheet of water is going to have larger surface area, and so it won't do that naturally. Here's that picture. We saw this guy in the video. That is a droplet of water in space, right? There's no gravity, and so the hydrogen bonding will cause the water to just clump up together, and it'll make one giant sphere of water. We have no gravity pulling on it, and so it's pretty much perfectly symmetrical. Here, you may have witnessed, a droplet of sodium hydroxide on the tip of your burette, and it's not a perfect sphere, is it? It's a teardrop shape, right? So it'll be shaped, kind of like this, where it's sticking to the tip, where you see water droplets from a faucet or something, and they're not spherical. That's because that's because gravity is pulling on it, and so the force of gravity is distorting the shape. But it wants to be a sphere, because it wants to minimize the surface area. And you see on this spider web, those little droplets are nearly perfect spheres. Any questions? Another property resulting from intermolecular forces is viscosity. Viscosity is the resistance of a liquid to flow. This is measured with a unit called a poise. It's a 1 gram per centimeter second. Just want you to have heard of that. I'm not going to do anything with it. So viscosity, the resistance to flow, is stronger in substances that have stronger intermolecular forces because they're more sticky, and so they can't slide past each other very much. So it's going to depend on molar mass, and polarity is also going to depend on the shape of the molecule. So here, if we look at that series of normal alkanes, pentane through nonane, here we have their formulas, and we see that nonane is longer, right? And there's rotation around the single bonds, and so these can interact over a greater area and become sort of tangled up inside of each other. And so the viscosity of nonane is higher, it's 0.77 versus pentane, which is 0.24. Viscosity also depends on temperature. The place you often hear viscosity in everyday life is on commercials for motor oil. They talk about, well, this one resists viscosity breakdown, right? Viscosity is important in your motor oil because the function of motor oil is to lubricate the moving parts of your engine. And it is a liquid, and so it will tend to fall down to the lower part of the engine. You want it to be able to coat the moving parts. So you don't want it to be very thin and flowing. You want it to be kind of sticky like syrup. So it's going to stay on the surfaces. So viscosity of the motor oil is important. And when you look at the numbers on motor oil, those numbers have to do with the viscosity. So viscosity changes with temperature because a higher temperature means higher thermal energy, higher kinetic energy. The particles are moving more. And they have more energy, and so they flow more easily, right? If you think of honey, and the honey's like really thick, it's very viscous. If you heat the honey up, it becomes more liquid, right? And easier to pour because it's at a higher temperature. Higher temperature means the viscosity goes down. So in your motor oil, you have to have a balance because if it's too viscous, it's going to gum up your engine. The parts aren't going to be able to move very well. But if it's not viscous enough, it'll just all run down into the oil pan and it won't lubricate anything. Tricky thing is, sometimes your motor's cold, and a lot of times while it's running, it's hot. So when it's hot, then the oil becomes less viscous and doesn't work as well. So they've done some really cool things with polymers in motor oil. So they've got polymers that will coil up at lower temperatures, so they become more spherical. The intermolecular forces between spherical molecules are not as strong. So at low temperatures, that decreases the viscosity. As you increase the temperature, these polymers uncoil and become more like spaghetti, long strands. And so then they're more sticky, and so they will stick together better, and the viscosity will be higher. And so using these polymers, you can moderate the changes in viscosity and have the oil work over a wide range of temperatures. Any questions? And what kind of a person figures that stuff out? A chemist, right? Chemists work in lots of different areas. You don't see them, right? But you see the results of their work. Another thing is capillary action. So here we have a person having blood drawn. So, you prick your finger, and there's the blood, and here's a capillary tube, and you touch it to the liquid, and the blood just runs up. Against gravity, how does that work? Well, that's capillary action. Capillary action is the ability of a liquid to flow against gravity up a narrow tube. And here we have illustrations. These are not blood. This is just red liquid. Here we see tubes of different diameters, and we see that in the smallest diameter tube, the liquid goes up higher than in a wider diameter tube. So there's two forces at work here. There are cohesive forces, and these are the forces, like hydrogen bonding, that hold the molecules to each other. And then there are adhesive forces, and that's the force of attraction between the liquid and the surface of the tube. So the attraction, the adhesive force, causes the liquid to creep up the tube. And the cohesive forces cause it to stay together. So adhesive force pulls some molecules up, and the cohesive force drags the rest of them up behind it. So adhesive force being strong, the liquid will rise. So depending on the identity of the liquid and the substance that the tube is made out of, you're going to get different amounts of capillary action. Capillary action is also the reason that we see a meniscus when we look at the volume of an aqueous solution in a burette or a graduated cylinder. The meniscus, it rises up at the sides. I think we've got a picture. Yeah. So here we have a meniscus. It rises up because water has stronger adhesive forces to the glass than it does cohesive forces, and so it creeps up. If you look at mercury in a test tube, you see that its meniscus goes the other way. It bulges up in the middle because mercury has stronger cohesive forces than adhesive forces. And so these guys are sticking together and they're pulling away from the glass. If you use a plastic graduated cylinder, you can notice that the meniscus is much flatter than in a glass one. If you're looking at different liquids like ethanol or hexane or something, they're going to have different shaped, what's the plural of meniscus? Meniscuses? I don't know. Have to look that up later. Any questions? Menisci? Yeah, I didn't want to say it. I don't know.